Okay, so now we're going to spend a little bit of time looking at when we are given numbers from other scientists, how we can identify how many significant figures are in that number. We did some experiments to show, or some exercises to show how we can determine how many significant figures we should be able to write based on measurements from tools. But now we want to know how many significant figures we should expect that there are based on numbers that are given us. And these are the rules. Any digit that's not a zero is a significant digit. So if it says 21.3, that's 3 significant digits. 2,134.56, 1, 2, 3, 4, 5, 6, that's 6 significant digits. And also zeros. If zeros are between non-zero numbers, those zeros are significant digits. Right? There was a way to measure something there, and it just happened to be a zero at that placeholder. Okay? Zeros. Say that again.
So 0 can't be the last digit if it's a significant figure?
That's a good question. And the answer is, and it's one of the rules, if I have this number, like 1,000, then these are not significant digits as it's written. So that's what we say. Zeros to the right are only significant if somebody has placed a decimal place there. So now those zeros are significant. That's where the decimal place helps me tell somebody else. Okay? So if I have this number, that has 0 significant figures. But if I have this number here, that has 4 significant figures. Or we call them sig figs. Okay? If there's zeros before, in between the decimal point and a significant figure, then those zeros are not counted. All right? And that's because there was nothing there to count. There's no material or measurement enough to fill in those numbers. So there can't be significant figures. If there's a zero afterwards, like that, then it is significant. And that's showing us that that last one is the estimate, right? So it has to be significant. But before, if there's nothing to fill it, then it's not significant. Now, up here where we had the 2, that was significant, so there is enough material. And then there's some zeros. Those zeros, again, are significant. But if there's just zeros here in the beginning, they're not significant. Again, this is what we just mentioned down below here. If you have a number like 300, that's just one significant figure. So the zeros at the end are not significant. Now, let me make sure you have heard of or teach you about what we call scientific notation. Scientific notation is a way of expressing numbers in a simplified way. So if I have this number, 567,000, all right? 567,000. Now that's a fine number, not a problem, not hard to say, but we can simplify it even more by making it a number between 1 and 10. A number between 1 and 10. So to do that, we put a decimal place here, 5.67. And then we count how many zeros, or how many decimal places we had to move our decimal to do that. We have to move it 1, 2, 3, 4, 5. And so we say 5.67 times 10 to the 5. So if I take 5.67 times 10 to the 5, that's actually equal to 567,000. All right? So this is called scientific notation. You choose a number between 1 and 10, and you move the decimal place over as the appropriate number to get the value that you're trying to represent. Now this becomes very useful for either very large or very small numbers. So for example, that number there. If I wanted to tell you that number, that would be a pain in the neck if I had to tell you every time. 0.000000000000135, right? Take a long time. So instead, I'm going to change it to a number between 1 and 10, which is going to be 1.35. And I count the decimal places. Can you help me count them?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
12. So 1.35 times 10 to the minus 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? So now those two numbers are the same number. So instead of saying 0.0000135, I can say 1.35 times 10 to the minus 12. All right? You want to practice? Can you write this number in scientific notation?
6.2
Uh-huh.
times 10 negative 3.
Very good. 6.2 times 10 to the negative 3. Fabulous job. And that's called scientific notation, and it helps us express large or small numbers. So I'm going to write a number in scientific notation here, and you're going to tell me what number it actually is, okay?
One, 3, 0, 0, 0, 0.
Like that?
Yeah.
So you started right here, and then you moved the decimal place how many times?
4.
1, 2, 3, 4. So shouldn't it stop there?
Oh yeah.
It doesn't have 4 zeros, does it? It moves the decimal place 4 times, right?
Right.
All right, so another way of saying 1.3 times 10 to the 4th is what? What number is that?
13,000.
Very good. Excellent job. So that is an important tool, especially when, for example, if I say, how many people were at the party that the government threw last week, and how many hamburgers does the government have to buy? There's a lot of people. It was 130,000 people. And the government says, we don't want to have 1,000 extra hamburgers just laying around. Are we sure it was 130,000 exactly? Or could it have been 129,000? Well, to express this with the appropriate significant digits, to tell somebody, right now, how many significant digits does this number have?
1, 2, 3.
It just has the 2, right? The 2 digits right there are significant. Okay? Zeros after are not significant unless there's a decimal point. So if there's only 2 significant digits, then this basically could mean that the 3 is the estimate. And if the 3 is the estimate, then it might be actually 1,200, and the government might be buying 10,000 more hamburgers than they need to. Or it might be 140,000, sorry. And then the government's not going to buy enough hamburgers. Right? And you don't want to be the government and not buy enough hamburgers or waste 10,000 hamburgers. And so you need to get more information. And so if I made this recording and I'm trying to tell the government how much they should buy, I want to let them know which digits are significant. And maybe these 4 digits right here are all significant. So the government only has to buy a couple hundred extra. But I don't have, we haven't talked about a way to tell somebody that there's 4 significant digits. What I can do, though, is use scientific notation to tell somebody how many significant digits there are. Because I can write 1.300 times 10 to the 1, 2, 3, 4, 5 times 10 to the 5. And so now this number here shows that there's 1, 2, and these zeros are significant. That's why they're there. They're showing, if they weren't significant, they wouldn't be there, especially after the decimal points, right? So that's showing that I have 4 significant digits, and that helps the government know where the estimate is. Okay, very good. So I'm going to show you some numbers, and you're going to tell me how many significant digits there are. What do you think? How many significant digits?
All of them.
That's right. 3 significant digits. Very good. How about this one? Is the 5 significant?
4.
That's right. 4 significant digits. Way to go, because this 0 down here is significant. That's why it's there after the decimal point. So therefore, they're all significant. How about this one? 1 significant digit. That's an estimate. So if somebody says there was like 1,000 bugs in the sky, there might have been 2,000. There might have been 900. They don't really know. That was their estimate. All right. What about this number here?
4.
Okay. It looks like 4, but this 0 here in front is not significant, right? There wasn't anything there to count. If there was something there to count, it could be significant. But there was nothing there to count. So it's just 3. Okay? Here's one more. This is kind of tricky.
5.
Very good. 5. 1, 2, 3, 4, 5. 5 significant digits. Excellent job. Now, this is the part that we've been working up to. When I perform math in my calculator, for example, I can put this problem into my calculator. 3.14 times 2.751 divided by 0.64. If I do that, the calculator spits out 13.49709375. But the calculator thinks that I'm just dealing with numbers. It doesn't know I'm dealing with measurements. These are actual measurements of something. And that there's a limit to the number of significant figures that my answer should have, because these are all measurements. And so, how many significant figures should I write? Well, it depends on the kind of math we're doing. This math is multiplication and division. So if we're doing multiplication and division, you look at all the numbers, you find the one that has the fewest significant digits, and then your answer has to have that many significant digits. So, which one of these 3 numbers has the fewest significant digits, or how many does it have?
What?
Of these 3 numbers here, which one has the fewest significant digits?
64. 0.64.
That's right, 0.64. How many significant digits is it?
2.
2. That's right. So the answer is not going to be 13.49709375. It's going to be, it has to only have 2 significant digits. So I go to the second significant digit, it's a 3, and I look to the right, and if the number to the right is 5 or higher, then I make this a 4. If it's not, I keep it as a 3. So the answer to the problem is 2 significant figures, and it's just 13. 13. All right? That's what we do when we have multiplication or division. We just look for the fewest number of significant figures, and our answer will have that many. And that's usually the most important rule to remember, because almost all of our work is going to be in terms of multiplication and division in this class. So, how many significant figures should result from this following problem? We're not. How many significant figures does this number have?
1, 3, 4.
4. How many significant figures does this number have?
5.
No, it's just the one. Just one significant figure, that 2. All the zeros in front are not significant figures. Does that make sense?
What?
Yes.
So 5.
So this has 5, and this one has 1. You always have to go with the one that has the fewest numbers when it's multiplication or division, right?
Right.
So how many is this answer going to have?
5.
No, 1 is fewer than 5, right? So the answer is going to be what?
None of these.
That's right. It's only going to have one significant figure. Okay, very good. That was multiplication. So in multiplication or division, you choose the fewest number of significant figures. In addition and subtraction, it's different. It's different for addition and subtraction. For addition and subtraction, you have to line your numbers up like this, where the decimal places are. Line your numbers up with the decimal places all lined together, and then you add them together in your calculator and find out what the answer is. And then you find out the one that stops having significant digits first, soonest. So this one right here stops at only one decimal place. So because of that, your answer has to stop at one decimal place. All right? Now, a lot of people remember this slide here and know that, oh yes, you choose the fewest number of significant figures. And so when they come to adding and subtracting, they just count. This has 4, this has 4, this has 4, so the answer must have 4. But that's not how you do it. You have to line them up like this and then cut off your answer at the one that has the fewest significant figures. Okay? So here's a problem. Let's do this problem together. I have 10.33, and I'm subtracting 0.0344. Now, do you have a calculator for us?
Yeah.
Can you do that in your calculator for us? 10.33 minus 0.0344. What does the calculator say?
10.2956.
All right, very good. 10.2956. Now, where is it that I cut off my significant figures?
2.
Right there?
Yeah.
So it's 10 point what? What am I going to write? 10.29, but the 5 means what? I change that 9?
Yeah.
To a 30, right? So my answer is 10.30. And how many significant figures does that have?
1, 2, 3, 4.
Very good, 4. So the answer is 4 significant figures. Okay? Now here's a hard one. Let's see if we can do this one together. Because what it is it's mixed math. We have to follow the order of operations. And I don't know if you remember the order of operations. It's please excuse my dear Aunt Sally, or PEMDAS, where you do the please. So I'm going to write down the acronym for us. First you do parentheses, then you do exponents, then you do multiplication, then division, then addition, and then subtraction. So here we do parentheses first. Well, actually in fractions you have to take care of the top before you take care of the bottom. So we do the parentheses first, multiplication there, and then we subtract that 12.2, and then we divide by the 2.2. So can you do that in the calculator for me? 10.0 times 10.88.
$108.8.
108.8. And how many significant digits should I keep? I have to look up here and see how many digits were in the different numbers. This one had how many significant digits?
3.
And this one over here?
4.
Okay, so how many do I get to keep?
3.
Very good. So what would my answer be if I only get to keep 3?
108.
Not 108, because this is higher than 5, so it goes up to what?
109.
Very good, very good. Now I do the next step. 109 minus the 12.2. Minus the 12.2. And remember, I have to line it up like this. Minus the 12.2. Can you put 109 minus... What's that?
97.
Very good. 97 point anything?
Well, it was 96.8, but then you turned it into 97.
Okay, good. 96.8, but you have to cut off it right there, and so it becomes 97. Very good. Now the last step is to divide by 2.2. What's 97 divided by 2.2?
44.
Okay. 44. Any other decimal places?
0.1.
Okay, 0.0909, like that?
Yeah, and 0909.
Uh-huh. And where do we cut it off at? How many significant digits do we get to keep?
2.
2. So, like you said, it's just 44. So, how many significant results? The answer is
2.
the 2. Right. Okay, very good. So, now we know how to communicate numbers to other scientists by letting them know our last significant digit is our estimate. All right, so that's a valuable tool. We are also able to receive numbers from other scientists and know where their estimate is based on the numbers that they provide us. Now, I'm going to introduce to you next a very important tool that we use in chemistry. And the tool is the number 1. The number 1. It's a very important tool. We can express this number in lots of different ways. Because if you take 2 divided by 2, what is that equal to?
1.
That's right. 3 divided by 3, what's that equal to?
1.
6 divided by 6?
1.
3.453 divided by 3.453? 1. Very good. So there's so many ways we can write the number 1. And what happens if I multiply a number by the number 1?
1.
So you're telling me that 7...
No, wait. It's whatever the number is.
Yeah, that's right. So if I take the number 7 and multiply it by 12.35 over 12.35, what is that going to be?
7.
That's right. Like you said, it's whatever the number is. Anytime you multiply a number by 1, it doesn't change the amount. The amount's the same. Now, because chemists know that, they use this tool here. They use the number 1 over 12 to be equal to 1. Is that true? Can 1 over 12 equal 1?
No.
No, it doesn't look like it, does it? But what if we say 1 foot over 12 inches? Are those the same?
Yes.
Yeah, those are the same, aren't they? Those are the same. And so what that does is if I take something like 7 feet and multiply it by 12 over 1, where this is 12 inches for every 1 foot, then my answer, 7 times 12, is that 82? 84. Well, 7 times 12 divided by 1 is going to be 84, but the difference is now my units, feet, cancel out, and I'm left with what? Inches. So that tells me that 84 inches is the same as 7 feet, because all I did was I multiplied it by, this is called a conversion factor. This on top is the same as that on the bottom. All I've done is I've found new units for this amount. So we use conversion factors because conversion factors are essentially the number 1. They're the same on top and the bottom. So here's a bunch of different conversion factors, right? I can say 1 foot over 12 inches, that equals 1. 12 inches over 1 foot, those are the same. 1,000 millimeters in 1 meter, that's fine. All right. There's one of these conversion factors that does not equal 1. Do you remember nanometers? Is that right? Is it a billion nanometers for every meter? Is that right?
Yeah.
That's right. How about inches? Which one's wrong?
The kilogram?
1 kilogram is 1,000,000 milligrams. I think 1 kilogram is 1,000 grams. So therefore it would be 1,000,000 milligrams. So I think that one's right.
Oh, wait. 2.54 inches. Centimeters equals 1 inch.
I think, isn't that right? Because isn't a centimeter kind of short, like that big, but an inch is like that big? So it's 1, 2.5. So this is 1 centimeter. And this here is 1 inch. So I think that's right.
Oh, 1 liter?
Yeah, that one's not right, is it? What's wrong with it?
The liter's bigger than milliliter.
That's right. I have my numbers flipped. It's supposed to be 1 liter is 1,000 milliliters. Or I can say 1,000 milliliters is 1 liter. You think people ever accidentally do that?
Yes.
Yeah, they do. That's a very, very common mistake that we make on accident. So we always have to look at our number and say, wait, is that true? Is 1,000 milliliters really a liter? We just think for a while and then we make our decision. So those are conversion factors. Very good. Let me run through an example of how we use conversion factors. Well, I think actually that's a good place to stop. We'll stop there. Next time we'll show you how we can use conversion factors to answer questions that we have. Okay, thank you. Goodbye.